Hello everyone, I'm Harmony, an assistant professor in the computer science department. My research is about theory behind quantum computing and quantum information. I'm especially interested in a universal model called quantum works. There are two types of quantum works, the continuous time and the discrete time. Both of them take place on graphs, so we can apply graph theory to study their behavior. In the continuous time quantum work, we can model a quantum system using a graph. The vertices are the qubits, and the edges denote their interactions. The whole system evolves according to the Schrödinger's equation, so there is a Hamiltonian edge that determines the transition matrix. Usually, we will initialize one of the qubits to the spin-up state, while the others will be initialized to the spin-down state. As we run the quantum work, these states are going to change. Here is an animation that shows how. If we stop the quantum work at time t, then those are the probabilities that we will find the qubits in the spin-up state. As you can see, at time π/2, the rightmost vertex gets the probability 1. That means the spin-up state has been completely transferred to the other side of the graph. This is called perfect state transfer. It's really useful in quantum information transmission, as well as designing swap gates in quantum circuits. Another interesting you might observe is that at time π/4, every vertex gets the same probability. That is called uniform mixing, and it generates desired inputs for many quantum algorithms. Finally, if we wait until time π, we will see that the leftmost vertex gets number 1 again. This is called periodicity. It means the initial state has been fully recovered. So all these phenomena are extremely useful, but the problem is they are very difficult to find. And even with some relaxations, these phenomena do not occur on most of the graphs. So the question is, how do we find out the graphs that do admit those phenomena? To answer that question, we will start by translating this quantum phenomenon into properties of graphs. Here is the adjacency matrix of the graph. It determines the evolution of a quantum work. And here is the decomposition of A into its eigenvalues and eigenprojections. It turns out every problem about the quantum work boils down to problems about these eigenthings. For example, if we want perfect state transfer to occur between the endpoints, then in every eigenprojection, the corresponding columns must be either equal to or opposite to each other. This is called strong cospectrality, and it's an intrinsic property of the graph that we can study without knowing any quantum physics. So what's next? Now that we have a characterization of this quantum phenomenon, we can use more tools from linear algebra, graph theory, number theory, group theory, and a lot of other areas to either find infinite families of examples or to show this will never occur on some class of graphs. And our team has been working on this direction for different Hamiltonians, ranging from the simplest adjacency model to the most complicated one that allows the qubit interactions to decay over distance. So that was the story about the continuous version of quantum works. The discrete version, on the other hand, are more related to the search problems. Imagine you have an unstructured database and you want to find a particular data point that satisfies some property f. In order to find the target, how many times do we have to evaluate f? Well, classically, this requires O(n) queries, because in the worst case, we have to check every possibility. However, there's a quantum algorithm due to Grover that solves this problem quadratically faster. And his algorithm is equivalent to running a discrete quantum work on that graph. Here, every vertex is a data point, and because we are in an unstructured database, we can move between any two data points. So the graph is complete. And Grover's search says if we start from everywhere simultaneously, run the quantum walk for roughly root n steps, and make a quantum measurement, then with very high probability, we will end up being on that special vertex. So that is one benefit about discrete quantum walks. They help us solve problems faster, including searching database, checking if all elements are distinct in a list, and detecting graph anomalies. Another cool thing about discrete quantum walks is that they actually build quantum computers. In a quantum circuit, we use qubits instead of bits, and we apply quantum gates instead of classical gates. And many of these gates can be constructed using discrete quantum walks. Finally, people have also used the theory of discrete quantum walks to study hard problems in combinatorics, such as graph isomorphism problem. So in practice, discrete quantum walks offer a lot of computational advantages. But in theory, how much do these advantages depend on the graph structure? For example, if I change my database to this structure, will a quantum search still offer speed up? And if so, by how much? It turns out those problems are not straightforward to answer, because first of all, a discrete quantum walk runs over the arcs of the graph rather than the vertices. That means even for a small graph like this, we will be dealing with a 30 by 30 transition matrix. Moreover, this transition matrix depends on not just the graph, but also something called quantum coins and shift matrix. For each choice of this pair, there is a different quantum walk on the same graph. And in general, we do not know how our choice will affect the performance of the quantum walk. So that is our goal. We want to translate these shift matrices and coin matrices into something manageable. And as a partial progress, our team was able to map some of them to embeddings of these graphs onto some services, as well as different graph operations, such as deleting a vertex, duplicating a vertex, and changing the weights on some arcs. And these reductions make it easier to identify graph properties that lead to quantum advantages. Back to our search example, if we compute the average success probability, we might observe something surprising. As the graph gets larger and larger, this average probability might not vanish. Instead, it could converge to a constant around 1/4. That means it doesn't matter if you have 40 vertices or 400 vertices. The average probability of finding that one target is roughly the same constant. And that's not a coincidence at all. Actually, we can use the second reduction on the right to prove this is true for many families of the so-called distance regular graphs. So that is a quick introduction to my research area. I hope you enjoyed the interactions between quantum and graphs. If you want to know more, here's my homepage and here's my email address. Feel free to reach out to me. Thank you.